Hi there, my name's Chris Collison, and today I'm going to talk about an experiment in Chem 155 where we're going to determine Avogadro's number. So how are we going to do that? Well, we're going to pass a current, a known value of a current, through a reaction solution, and this electrochemical solution is going to generate hydrogen gas through a reduction of protons, through a reduction of the H plus ions that we find in sulfuric acid, in fact. And we're going to generate this hydrogen at a copper electrode that's actually submerged in a way such that the bubbles that are generated will float up into this inverted Bunsen tube, we're going to call this. So these bubbles float to the top, and we're going to collect that hydrogen gas. We're going to be able to measure how much gas is collected. And in this video that I'm going to show you now, I'm going to talk about all the measurements we're going to make. The temperature, how we're going to calculate the pressure of that gas, think about the volume of that gas. So inevitably, we're going to use the ideal gas equation, PV equals nRT. We're also going to think about how much charge is passed through the reaction. So Q, the charge, is equal to current multiplied by time, Q equals IT. And we're also going to think about the Faraday constant, which equates 1 mole of electrons that's required to neutralize 1 mole of protons. So that 1 mole of electrons has a certain charge, so we can connect it with the current and the time that we're actually running this current through the experiment. So these are the measurements we're going to collect in this experiment today. And it's going to be very powerful, and we'll ultimately come up with a measurement for Avogadro's number, and we'll see how that number compares to the known value from the literature that we all know and love. So I hope you enjoy the presentation today. Get your Excel spreadsheets out, and I look forward to seeing you in lab, and hopefully we'll fully understand what's going on. It'll be quite an intense process to pack it all in, but we can do it with this understanding behind us. So thanks for listening, and see you in lab. So here's a standard Excel spreadsheet that you're going to be provided with, and it's not filled out at all in the version that you're seeing in front of you. What I'm going to ask that you all do is to write down the equations that are important in this area around here. And so there are certain cells that are left available to you. What we're going to try and fill this in step by step. We're going to think about some of the measurements that are made. So for example, we can look at the colors of these cells in here, and they're color coded such that the ones that are orange are going to be the measurements that you make. The white cells in here, we're going to add in some equations, and these are the values in here that we want to pull out at the end of the experiment. I'm actually going to expand this spreadsheet a little bit to include some differences in the height of the liquid that you'll have in your tube. But we'll come to those as we work through the spreadsheet. So for now, what we're going to do is basically remember to measure the temperature of the lab. Most of the time, in fact all the time in science, we're going to use degrees Celsius. You could of course also work in Fahrenheit, but it becomes a little harder to work with Fahrenheit. But just to keep this interesting, don't use Fahrenheit, but I'm going to show you how we might convert from Fahrenheit. So we're going to put in 75 in here. So we've measured the lab temperature to be 75 degrees Fahrenheit. You're going to measure it independently. How do we calculate the temperature in Kelvin? Well, what we need to do is recognize that a Kelvin temperature of 0 degrees Celsius or 32 degrees Fahrenheit is equal to 273.15. And then I'm going to add to this, in fact I'm going to add to this B2, so the cell B2, which is our temperature in Fahrenheit, minus 32, and then to convert B2 into Celsius we're going to multiply this number by 5 divided by 9. There's the conversion into Celsius and then the conversion into Kelvin. The other thing you're going to do is you're going to measure the total amount of time that you're conducting the experiment, that you're passing a current through the system. So we're going to write down, for example, a time. Let's imagine we've run our experiment for 145 seconds. So we're going to add that in. The current you're going to try to keep fixed. So let's imagine we've run the experiment at a fixed current of 1.5 amps. And you'll notice that the units are provided in column A along with the measurement that you're making. The height of the liquid in the tube. So we're going to put in here, right in this place, we're going to actually put the final height of the tube. And I'll explain in a little bit why this is important. So we're going to put the final height of the liquid in the tube. And maybe this also reminds us that we should also collect the initial height of the liquid in the tube. So let's put that final height in the tube, and we've measured that to be 245, and that's millimeters above the liquid in the beaker. So that's the final height of the liquid in the tube. The volume of the gas in the tube, let's suppose that we measure that to be 37.9. We're going to find there's lines on the side of the tube so you can figure out what the volume is. So we're going to make an assessment and say that's 37.9 milliliters. We're also going to provide the pressure of the room, and we're going to provide this in millimeters of mercury. So we'll call this 767. Okay, and this is where I'm going to add a couple of rows in here. So right click, add, insert 2 rows. And on the first row, I'm going to recognize that we will be interested in the initial height of the liquid in the tube. And we're also going to add in here an initial volume of gas in the tube in milliliters. So we will say that the initial height of the liquid in the tube above the liquid level in the beaker, we're going to say that we've measured that to be 600 millimeters, not milliliters. And the initial volume of the gas in the tube, we're going to say, is 2.3, and that's in milliliters. So what do we do with this now? Well, the first thing we're going to do is we're going to calculate the total number of coulombs that were passed through our cell. And this, as I've mentioned before, is simply equal to Q equals IT. So, for example, we can write down Q equals IT in here. And that's going to help us because up here the total number of coulombs is going to be equal to, that's the charge, it's going to be equal to the current in amps that we find in cell B5, and we're going to multiply that by the time in seconds that we pass that current through the system. So there is a total number of coulombs, it's 217.5. So the total number of electrons transferred is what we need to calculate. Next, we're actually going to divide the measured number of coulombs. So we're actually going to think about the number of coulombs. It's 217.5. We're going to divide that by the number of coulombs per electron, and that's actually going to tell us how many electrons were transferred. So the number of coulombs per electron is equal to 1.6022, and that's times 10 to the negative 19. So we enter that number in, and we end up finding a total number of electrons transferred is about 1.36 times 10 to the 21, and that's number of electrons. Now, well, this is the point where I'm going to modify the sheet a little bit. I'm going to insert room for 4 additional entries. And I'm going to type in here the pressure of all gases in the tube initially. Okay, so I've added the following measurements. Pressure of all gases in the tube initially, the pressure of the air that's in that tube. We're going to then convert that air pressure into atmospheres, the units of atmospheres. We're also going to calculate the number of moles of air, and these are all initial values before we've ever passed any current through the system. So we're going to account for any air just in case we don't fill up that tube completely with sulfuric acid, and this is quite typical. So let's account for that right off the bat. So if we go back to the PowerPoint slides associated with pressures in liquids, what we find is that we need to be able to measure the pressure of the air at the top of the tube. So really what happens is we have a beaker, and here's our sulfuric acid, and we've got liquid in here. And what happens is we've got our sulfuric acid that sits over the top of the water level, but we also have, if we haven't completely filled up this tube with liquid, we've got some air at the top of this tube, and we need to account for the volume of that air in order to know how much gas actually came from the reaction. So in our reaction, we had a copper wire in here, and from that copper wire that was hooked up to our electrodes, what happens was we get bubbles that float up to the surface, and those bubbles we collect in the top, but we want to make sure that we count first for the amount of air that's in the top of that tube before we ever pass current through that copper, and before we ever start adding hydrogen gas to form that mixture. So the pressure of all the gases in the tube initially is going to come down to the initial pressure. So we're going to say, of course, we remember the initial pressure as being the pressure in the room is in B8, and we're going to subtract from that B9. We have this height, and this height initially we're saying is 600 millimeters. So B8 minus 600 millimeters, but that's millimeters of water, so we have to convert this into millimeters of mercury. So we simply take the density of water and we divide that by the density of mercury, which is 13.546, and we end up having a pressure of all the gases in the tube in terms of millimeters of mercury. Now, the pressure of the air in that tube must also take into account the vapor pressure of the water. And the vapor pressure of the water, if we look up, by the way, and you have to go and do this for the actual temperature in the room, but supposing that the temperature in the room now is 24 degrees Celsius or 75 degrees Fahrenheit, well, we find that the vapor pressure of water in that case is 22.4, and that's millimeters of mercury. So what we're going to do is subtract that value, and we'll do that in cell B15. So we end up having here equals B14 minus 22.4, the vapor pressure of water, which you're going to look up. Okay, and now we're going to convert this air pressure into atmospheres, and the way we do that is we take that pressure, so it is equal to B15, and the conversion factor that we're going to use is 760, because there is 760 millimeters of mercury for 1 atmosphere, and so that ends up being a fairly straightforward conversion. And so we find that the pressure of the air that's already in that tube is 0.92 atmospheres. Now we want to come back and think about the ideal gas equation here. So the number of moles of air in that tube is going to be simply equal to, so it's the pressure times the volume divided by the ideal gas constant divided by the temperature. So that's equal to the pressure, which is B16, and that is multiplied by the volume. So we previously measured the volume, and it's up here in cell B10, and then that's going to be divided by the ideal gas constant, and we'll write that down as 0.08206, and that's multiplied by the temperature, which we have in Kelvin, that's in cell B3. So now we obtain the number of moles of air that were in the tube before we started passing current through our copper wire. Next up, we're going to calculate the pressure of all the gases within the tube once the experiment is complete. So we're going to follow a similar approach here, but this time we're going to start with, again, we're going to start with the pressure in the room, which is B8 in here. So we're going to say equals B8, and we're going to subtract from that now the final height of the tube, which is going to be in B6, cell B6, just like we did before. And then we're going to multiply that value. We've got to take that value, which is the number of millimeters of water, and we've got to convert that into millimeters of mercury. So that ends up being multiplied by 1 divided by the density of mercury, which is 13.546. So now we of course want to find the pressure of the hydrogen gas that we've collected. So first of all, let's subtract the vapor pressure of the water. And the vapor pressure of the water again is 22.4, and that's in millimeters of mercury. We're going to make a couple of corrections at this point. We're actually going to call this the apparent pressure of the hydrogen gas. We recall that there's also some air in there, and I'm just remembering there is an error from earlier on. When we calculated the number of moles of air, we took the volume in here, B10, and that was given in milliliters. So we actually have to account for the fact that this is in milliliters, and we need that to be in liters. So we're going to put a divide by 1000 in here, and we're going to put some brackets around that, and we'll end up recognizing that we were off by a factor of about 1000. Okay, so that will have a ripple effect. So the apparent pressure, coming back to the apparent pressure of this hydrogen gas, this is going to simply be equal to the pressure of all the gases. We're going to subtract the vapor pressure of the water in here, which is 22.4 millimeters of mercury. We're going to convert this apparent pressure into atmosphere. So again, I'm going to say the apparent H2 pressure into atmospheres. And we can easily do that again by remembering that 1 atmosphere is equal to 760 millimeters of mercury. So we'll take the value from B19 and subtract that by 760. Lo and behold, we have our pressure in atmospheres. And finally, we're going to calculate the number of moles of hydrogen gas produced, the actual number of moles of hydrogen gas produced. And it's here that we're going to ultimately subtract the number of moles of air that we had to begin with. But let's first of all calculate how many moles of all gases we have in this tube now. And that comes down to the pressure that we've measured, and that's in cell B20. And we're going to multiply that by the volume of the gas in the tube, and that's the final volume of the gas in the tube. So that's 37.9 divided by, that's now divided by 1000, because we need to convert this into liters. So that's our pressure times volume. And what we're going to next do is divide that by the ideal gas constant, and that ideal gas constant is 0.08206, and that's going to be multiplied by cell B3, which again is the temperature, and we're going to put that all in brackets. So this is the total number of moles according to the ideal gas equation that are in that particular inverted tube, right? But now we're going to subtract the number of moles that we had in there to begin with, and that number of moles there in there to begin with is up here in cell B17. What we're going to do is go through and check and make sure that we've calculated everything through correctly. And lastly, what we're going to do is calculate the number of moles of electrons that would, of course, be needed in order to convert hydrogen ions into hydrogen gas. So if we now know the number of moles of hydrogen gas that we produced, that's up here in cell B22, well, we know we need 2 electrons for every molecule of hydrogen, because hydrogen molecules, the formula is H2, so there's 2 atoms of hydrogen for every molecule of hydrogen gas. So we're effectively going to take this number of moles and we're going to multiply it by 2. And there's our number of moles of electrons. Finally, we're going to calculate Avogadro's number. So of course we know how many electrons we transferred. Okay, we calculated that up here. So here's the number of electrons that were transferred. So that number is given up here. And we're going to divide that number by the number of moles of electrons that were actually needed to give us 0.0014 moles of hydrogen gas. So we multiply that number and we come up with a number in this particular example of 4.85 times 10 to the 23. It's not exactly 6.022 times 10 to the 23, but it's pretty darn close. We can also write down the uncertainty, the percent uncertainty. So of course we know what Avogadro's number is. So the way we can do this is simply to write down Avogadro's number 6.022 times 10 to the 23 minus B26. And we can find out that we're about 20% uncertain. That's one way we can look at the percentage uncertainty on this particular experiment. So that concludes our work on the first column in here. What I want you to do is to annotate and write down all the equations that you're using up here and follow through my Excel spreadsheet. You'll start to see how those measurements that you make tie into these calculations, and you'll be able to describe that appropriately in your lab report and in your abstract. So thanks for listening. We'll come back to this next part of the Excel spreadsheet in the next video. Thanks for listening.